Okay, so in this video, we're gonna learn permutation groups. All right. So permutation, let me define permutation first. So let's say S is a finite set, and then a permutation of this, of a finite set S, is simply a bijection, say bijection from this set to itself. Here, a bijection means a function that is one-to-one and onto. So one-to-one and onto function. That's what bijection means. So permutation is just a one-to-one and onto function from this set to itself. So that's the definition of permutation. So example, so if S equals 1, 2, 3, and if you take a say a function pi from S to S defined by pi 1 equals 2, pi 2 equals 3, pi 3 equals 1, then this is a bijection. So then pi is a permutation. Okay, there are many ways to represent a permutation, but we will consider two-line notation. So if pi is a permutation of a set, bracket n is a shorthand for the set of integers 1 to 3 up to n. If pi is a permutation of n, then we write pi like a matrix. It looks like a matrix, 2 by n matrix, like this. Pi of 1, pi of 2, dot dot dot, pi of n. And this is called a two-line notation. So we're gonna use this two-line notation, which is quite useful if you consider pi as a function. So for instance, if pi is given above, then we can write pi as this two-line notation. So pi of 1 equals 2, so we write 2 here below 1, and pi of 2 equals 3, so we write 3 below 2, pi of 3 equals 1, so we write 1 below 3. So the first row is always 1, 2, 3 up to n in this increasing order, and the second row will represent pi. Okay, all right, and because pi is a permutation, we can consider compositions of them. So composition of permutations. So definition. So pi and sigma, let's say they are permutations of the same set n, say. Then the composition of pi and sigma is again a permutation. Is the permutation, let's denote pi circle sigma. It's actually a function, but it's easy to see that it becomes a permutation defined by the usual composition of functions. Pi circle sigma of I is equal to pi of sigma of I. So this is the definition of a composition. So the usual composition as a function. So let me give you an example. If pi is in two-line notation 1, 2, 3, 2, 3, 1, and sigma 1, 2, 3, say 1, 3, 2. Then pi circle sigma, composition of them. To compute this, we use just the definition. We first compute sigma 1 equals 1, so it's pi of 1 equals 2. So the sigma the composition takes 1 to 2, and for this we just use the definition. Sigma of 2 equals 3, so it's going to be pi of 3, which is 1, and this is equal to sigma of 3 equals 2, pi of 2 equals 3. So this again is a permutation, and actually it's easy to see that composition is always a permutation if the two functions are permutations. Note that in general, so warning, sigma compose pi is not equal to pi compose sigma. So the order of the composition is important. All right. Now let me give you a definition of the identity permutation. Identity permutation of n is the permutation. We will denote this by ID n to n, given by this. As you can imagine, it takes every number to itself. So identity function really. And now we can define the inverse of the function or permutation. The inverse of a permutation of n is the permutation sigma such that if you compose sigma with pi in both ways, they are equal to the identity permutation. And the inverse is usually denoted pi inverse like this. So example, let's consider n equals 3. Then identity permutation is in two-line notation. It's just 1, 2, 3, 1, 2, 3. And if you consider the pi that we had before, then you can check that pi inverse is 3, 1, 2. You can check that if you compose these two permutations, we get the identity. And because pi is a permutation is a one-to-one map, one-to-one map, it always has the inverse. The inverse is in fact the inverse function. It's the same. The inverse of pi, this really is the inverse function. The same thing, function of pi. All right. Now the title of this lecture was permutation group, so we need to define what they are. A permutation group is a set, say G, set of permutations. Say permutations of n satisfying the following condition. Satisfying the following conditions. There are several conditions. Let's say properties. Following properties. So the first property is called identity property. And that means that the identity permutation must be in the set. And the second, inverse property. It means if pi is in a permutation in the set G, then pi inverse must be in the set G. The third, closure property. If two permutations pi and sigma in G, then their composition must be in G. So if a set of permutations satisfies these three properties, and is called a permutation group. Permutation group. All right. And there are many interesting permutation groups, and one of the simplest but also very important is this group of all permutation. Group of all permutations of n is called the symmetric group. So if we collect all the permutations of n, and it satisfies these three properties, identities there. For every permutation, the inverse is also a permutation of n, and if you take the composition of two permutations, we get a permutation. So it satisfies three properties, so it becomes a group, and it's a permutation group. It's called symmetric group. And in fact, in group theory, when we define group in a more abstract way, we can define groups in more abstract way, but for our purpose, this definition is enough. But just for a side note, let me mention, in group, there should be a property called associative law, and it's actually automatic for permutations, because this is composition. The operation is the composition, and because this is the composition of functions, the associative law is immediate. So associative law means if you have three permutations, pi, sigma, and rho, and if you take the compositions like this, there's two ways to compute. There are two different ways to compose three permutations, but they become the same thing. And this is called the associative law, and this is true because this composition, they both are in fact pi, sigma. I'm not going to say this for the details, but it's very easy to see this because both as a function, if you want to know which integer I gets sent by these two permutations, then they all get sent to this number. Okay. And the last slide, I'm going to tell you on one very important group called dihedral group. very important group, especially for our purpose, because we want to do some symmetric class of n-gon. So an example is quite simple. Let me begin with a simple example. So suppose that we have a square with 4 vertices labeled 1, 2, 3, 4. And now I want you to consider all configurations uh, obtained by rotating or reflecting this square. But we don't want to change the shape of this square. This square must be in this shape. So one possibility, like 90-degree rotation, it will be 1, 2, 3, 4 like this, and 180 rotation will give us 4 vertices, for vertex labels like this, and 270 and 360, which is really the same as 0 rotation. That means we don't do anything, so it means do nothing. So doing nothing, so it stays the same. So there are 4 rotations, and there are reflections. If you reflect about this axis, 1, 2 will change their positions, 3, 4 will change their positions. And also we can reflect about this line, 1, 4 will change their positions, 2, 3. And there are also more. We can rotate or reflect about this line, then 1, 3 will remain their positions, but 2, 4 will be changed. And the final one is the reflection about this axis, and 2, 4 will stay the same position, but 3, 1 will be changed. So there are 4 rotations and 4 reflections like this, and we can write the corresponding permutations in 2-line notation. Let's say here 1, if you rotate this about 90-degree clockwise, 1 is now here, which is in the second position. 1, 2, 3, 4, second position. So I'm gonna say 1 gets sent to 2 by this rotation, and 2 is now in the position of 3, so it's 3, it's 4, and 1. And here 1 is in the position of 3, so it's 3, and 2 is in the position of 4, so it's like this. And for this, 1 is in the position of 4, 2 is in the position of 1, and 3 and 4 like this. 1 is there, just its position, so like this. And for this, 1 and 2, they change their positions, so it's gonna be like this. And for this, 1 and 4 change their positions, it's like this. 1, 3 are in their positions, and 4, 2 change their positions. 2, 4 stay the same. 3, 1 change their positions. So we have 8 rotations or reflections, and they all correspond to permutation. And these 8 permutations, in fact, form a permutation group. You can check that they all satisfy. If you collect them all, then that collection satisfies the 3 conditions: identity, inverse, and closure property. So it's going to be a group. And dihedral group Let me finish this by giving you the definition. So dihedral group denoted D sub n is the permutation group obtained in this way. Permutation group coming from rotations and reflections over regular n-gon. So here, if you collect them all for this will give us a D4. And similarly, we can consider D5, D6, etc. And this defined to be it's called dihedral group. Okay, this is the end of the video. Thank you.